Okay, well, welcome to this session on Polygon and Polyhedron. This will be essentially the second part of an earlier presentation on geometry, functional geometry in version 12. And we decided to have a special session for Polygon and Polyhedron because of the large set of features and the general approach and future vision we have related to those objects. So this talk, essentially, I will first talk about polygons, the new polygon with holes we added in version 12, as well as a set of functionality. And after that, we'll talk about polyhedron, which is the new primitive we added, which represents an actual polyhedron, and the set of operation around them. As usual, when we have new object like that, we have a set of property we build around them, and then we have a set of solver you can use to operate, like solve an equation or compute an integral on top of it. So let's start with Polygon. So in version 12, we added broad support for polygons, especially polygon with holes, and it worked nicely in the geometry frameworks as well as the graphic framework. So this is just a basic example where you use our country data to get a set of coordinates of South Africa. As you know, South Africa have Lesotho inside. So you can take the coordinate of South Africa and then take the coordinate of Lesotho and just use polygon and do a outer, which represents kind of the outer boundary of South Africa, and then the inner part, which is the boundary of Lesotho. So when you evaluate it, you get a polygon object. And actually, if you do a graphic of that, you have that nice plot of South Africa and Lesotho inside. One first thing you should notice, right, is that in 12, the typesetting, or we added typesetting for polygons. Now it returns you a nice summary box with general information about your polygon. You can open it and then you get the type. If it's a polygon with holes, you get the boundary, as well as some basic measure, like in this case, the area. And all that is computed in daily evaluation and such. So it shouldn't in principle affect any of your work if you just compute polygon in general. So this kind of one base idea of the polygon with holes, where the specification is essentially the outer followed by the inner using the rule notation. And in general, you can specify several inner boundary. So yeah, several, you have one outer boundary and you can specify several inner boundary for your polygon. And also you can use essentially the graphic complex notation we have, where you have a set of points, and then after that you have it, data which are essentially a collection of indices. So which is kind of a more compact representation. So let's take an example here where you have a polygon which is a set of self-intersecting line. So you see already that in the typesetting we kind of show you that that polygon have a hole. So we kind of do, roughly speaking, a recrossing operation there. So we detect what is inside and what is outside. But you can also use a canonical polygon for that. And what canonical polygon does is that it represents it as a set of points, so like that graphic complex representation, followed by the indices. So this is the outer boundary, and that's the inner boundary. And if you use outer polygon and inner polygon, you actually get explicitly the outer boundary and the inner boundary. And a lot of operation we have actually implemented on polygon essentially rely on that decomposition, right? Because if essentially you take an outer boundary or inner boundary, usually they are weakly sample. So you just have basic intersection, so that allow you to actually apply a lot of geometric operation on them. So in this case, we can easily compute the area of that polygon with hole by just computing the area of the outer boundary, and then you subtract the area of the inner boundary. So this is kind of just a representation of a polygon, with the new syntax in the language. The old syntax, where you just give a set of points, and it's still working in the system essentially. But one key thing also we want to do, especially in geometry, is to notice that a polygon is a general object, even if the head is not polygon. For example, a rectangle is a polygon, right? Or you can represent a polygon as an implicit region. So what we try to do is to enhance a function like canonical polygon to actually do that. So in this case, let me see if I can actually do that here. I can take canonical polygon, I can give him a rectangle, and you can recognize that is an actual polygon and return you the actual form or that canonical form using the coordinate as well as the indices. And we hope that in the future version, we kind of enhance more canonical polygon to actually recognize more objects which are polygon essentially, which have linear boundaries, and that we kind of enhance the whole framework. So all operations which normally will work on polygon, we also work on those objects. And later on, I will actually show you a separate example where we do that general mapping for polygon. So what we also try to do is, besides just introducing a new notation, we added a more constructor to allow you to actually construct polygons. As you know, when you have a sample polygon, essentially the boundary don't intersect, the definition of a polygon is well known. I mean, there is no really ambiguity there. Everybody agree that when a point is inside that closed counter line segment, closed line segment, that means those points are in the polygon. And when a point is outside that counter, the points are outside. They are not in the polygon. But when you have self-intersecting polygons, it gets more complicated. So what's a point, what's the inside part of a polygon, what's the outside part, or when can you say a point is inside the polygon or not? So like if you see in this case, when you have this set of counter lines, what is the point, what's the inside of the polygon or what's the outside of the polygon? So using our standard definition of polygon we have since the introduction of polygon, if you actually do that, in this case, we generate that, you get actually this set, which is kind of the full set, completely closed set of points. But you can also run a ray tracing fully, and what you get is actually this polygon. I mean, this is just an illustration of that up here, where you actually have holes inside. Or you can actually also do a winding count or winding number, and then you get also this polygon. So you see that in those three cases, what we get actually different polygon. So those depend on the different definition of what people adopt. So there is ray tracing, there is winding number, and such. So in version 12, we introduce those functions. So crossing polygon will give you the polygon based on the ray tracing. So if you take a point, any point, and you draw a ray to infinity, you count the number of intersections. If the number of intersections is odd with respect to the boundary, so the point is inside. If it's even or zero, it's outside. And winding number is roughly the same case. If you have a point and the boundary wind around it in a, depending on the hole. In this case, it's 2 holes. So you wind around twice. That means the point is inside. Otherwise, it's outside. So that gives us kind of a different way to define a polygon. And what we do behind the scene is that we take those counter point, those counter, as well as this point, the end point, and we do the appropriate operation, and then we return you the canonical form, which is the set of points followed by the indices. So that kind of allows us to unify all those concepts of polygon, all those definitions into one. So you can, depending on the system or depending of what you learn in terms of polygon with intersection, you can just use it in the version 12, and we do everything appropriately. Another constructor we added is random polygons, or we added a suite of generation of random polygon. As you can imagine, those are kind of useful if you want to study property of polygon like convexity, sample, and such. So here we have a random generator. So in this case, I generate 10,000 polygon, convex polygon. I can compute the area. And as you know, theoretically, we know that the area will follow a normal distribution. So you can use our probability and statistic framework to estimate the distribution. So here you get the normal distribution with appropriate coefficient, and then you can actually plot it, and then you see that actually your sample actually follow the normal distributions. So if you look in the documentation of random polygon, which I will open here, random. So we have an extensive syntax where you can give the number of points, and you can also specify the dimension. So you can say, you want a polygon in dimension 3 or dimension 20. We'll generate it uniformly. And we can generate polygon with convex shape, simple, star-shaped, or we can compute actually the convex hole based on a given distribution. So you can actually use any of our distribution functionality we have. So you can, for example, you can see uniformly over a square and such a thing. So this is kind of the set of functionality for our polygon we have in version 12. Oops. Back there. So now, so that was essentially constructor. So we have crossing polygon, 1D polygon, and we have random polygon. But also we added function to do the composition of polygon. As you know, usually when you want to do operation, or depending on what you want to compute or operation, is usually you know that if you decompose the polygon into simple form or convex form, you have a more optimized way to compute a property, for example, or do some operation. So what we did is that we provided a general function called Polygon Decomposition to actually do that. So you can actually take your polygon, you can feed him a polygon and say, well, you want a decomposition into simple convex, and we return you a decomposition in terms of simple polygon or convex polygons. So this example kind of show you essentially how you can actually use those decomposition to to solve the art gallery problem, where essentially you want to find the minimal number of guards which can actually observe the whole gallery at once. So if you take an image, for example, of a plan of your gallery, for example, this is the gallery, you can convert the image into a mesh, and here actually you can apply canonicalized polygon. As I told you earlier, canonicalized polygon will look at the mesh and recognize that it's an actual polygon, and it will convert it into the canonical form. So the index, point followed by the index. And from that canonical polygon, you can actually run the decomposition. So in this case, we decompose it in terms of triangles. So let me actually remove the semicolon there. So there is a decomposition in terms of triangles. So you have a bunch of triangles there, and you can actually plot it. So you see the graphic actually show you the same form of the original polygon. And you can use our graph framework to actually generate a relational graph between those different triangles. So which essentially connect, if you look at it roughly speaking, they are the face of your mesh or your polygons. And from there, you can actually do a step first and actually solve the art gallery problem. So in this case, you have the set of possible position of your yard. And if you actually compute it at the end, you get the minimal set, which are the different positions you should actually put your yard to actually observe your gallery uniformly. So this example just show you how you can essentially use our image processing, jump to our general geometry, come back to polygons, use our graph framework to solve actual useful problem. Okay, so this is essentially about polygon decomposition. You can actually look at the documentation of that page and see all the variety of decomposition we actually have. So convex, triangle, and such. Okay, so now let's move to the next new object we introduced in version 12, which is polyhedrons. So this is completely new. So if, for example, I take the spiky, the standard logo of the Wolfram Alpha, now it actually automatically return you a polyhedron object before it will return you a list of faces of polygons. So if you take that object, you can actually feed it to graphics, graphic 3D, so you get an actual polygon object. And it's also an actual region. So if you put it in the region, it automatically visualizes into this nice object. And from it, you can actually compute property. So similar as Polygon, we also added a summary box where you get a nice summary, the number of points, the number of faces, the actual embedding dimensions. As you can imagine, we support polyhedron in any dimensions. And we hope to actually add more property to actually make it work in more higher dimensions. In this current version, we kind of more focus on dimension 3, which is kind of the standard dimensions. And also you get some of the standard measure, the boundary and the volume of your polyhedron. So now let's look a little bit about that representation of polyhedron. As you can imagine, we try to keep stuff consistent in the system. So what we did is that we made consistent the representation of polygon and polyhedron to be actually quite similar. So if I, for example, open the documentation of those two objects, so here I will take polyhedron. So the polyhedron take a set of faces. Similarly, a polygon take a set of points. So we have the rule which represent the void in the case of the polyhedron. We have here a collection of polyhedron, and then we have the index representation. So the data, a set of points followed by the index, kind of a compact representation. As you see, this is also kind of similar to what we have in Polygon. So we try to keep all of those consistent. And also that documentation kind of goes extensively to detail, the different behavior, especially when you have intersecting faces and such. So you can take a look at it and get a more clear idea. And besides just introducing the standard polyhedron object, we also introduce other, the different platonic solid objects. So just to, have all the different basic constructor people use in geometry. So in earlier version, we have tetrahedron. So in this version, we added cube, octahedron, dodecahedron, and icosahedron. And those constructors are kind of similar in the sense of, in terms of argument they take, as well as the representation. So let me show you one basic case, which is cube. So in cube, essentially, you can specify it, with no argument. That represents kind of the basic, unit edge length cube. So the length is 1. But also you can specify the length by L, right? Or you can specify the center or the rotation of your cube. So that syntax also applies to all the platonic solids. So that's kind of easy for modeling, right? So as you can imagine, usually our constructor are represented in terms of point and corner point and such. So in this case, we kind of focus more in terms of modeling, where you take, you describe your cube in terms of length. You can rotate it or adjust it, translate it, and position it in space and such. So I will take a short break and just look if there is any question in our live stream. Well, I believe right now there is not yet any question, so let's just continue. So as I also say, we try to make all the frameworks similar. So you just use the functionality. If you know already how Polygon works, you can imagine how polyhedron work and such. So in the case of polyhedron, we also introduce canonical polyhedron. As you can imagine, if you take a polyhedron and write it or convert it to the canonical form, the index form. So point followed by indices. So in this case, I take a cube and evaluate it, and I get an actual polyhedron object. So if I look at the input form of this cube, there I see actually the actual corner point, which are 8, followed by the indices, which represent the different phases of your polyhedron. So you can also fit a canonical polyhedron in your object, a mesh region, for example, a boundary mesh region, or even an implicit region. And we try our best to automatically detect that is the polyhedron and give you that canonical representation. And you can imagine that kind of quite useful, especially if you are writing code which manipulate polyhedron. So you can actually canonicalize it to a standard form and manipulate it. And it's roughly the way we actually do the implementation internally. We take any input you provide us, we try to canonicalize it, and then we use that canonical form throughout the code after that. Okay, now let's see in terms of operation what we have. Well, one set of operation we introduce is what is usually called the Conway notations, which essentially about 13 operations, but we reduce it in the current version to essentially the five basic crucial ones. And they're essentially augmented polyhedron, beveling polyhedron, truncated polyhedron, snub polyhedron, as well as the dual of a polyhedron. So these are kind of the basic operation, and you can compose it to get actually all the Conway notation operation, essentially. So in this case, we can compute the dual of the dodecahedron. So as you can imagine, we kind of internally symbolically recognize that is a dodecahedron, and then we know that the result will be an icosahedron. So we return you to actually icosahedron with the appropriate edge length. And one thing to notice actually, that the dual we return is actually, roughly speaking, the topological dual. And essentially what we do is that the point, the end point of that dual, we pick it to be the center of the center faces. So for each face, we pick the center has the actually corner point of a dual. We can actually pick other position, so that will make you a more different dual operation. But we kind of pick in this case to return the topological dual. And also that will satisfy obviously some of the basic property, like in this case, where you actually see it nicely embedded inside. So as I said, we have augmented polyhedron, bevel polyhedron, truncated polyhedron, and the snub polyhedron operation. And you can actually combine them to make them work. But one thing I will actually want to emphasize and point out is that we actually make them work on arbitrary, I would say, objects, which are not even per se valid geometric objects, where you may have actually self-intersections. So we did that essentially to give you the ability to manipulate graphic results and have some nice visualization, right? Because there are cases where if you do a sequence of operation, the resulting faces may be degenerate, right? They may be non-coplanar, they may be, self-intersection and such. But, still those operations, we take them and do the operation and you can use it in graphics. But in some cases, they may not be actually currently valid geometric region, 3D geometric regions. So, and in the next future, we hope that we actually provide more functionality to actually do the appropriate repair, right? When you have, for example, non-coplanar faces and such, to actually do the cleaning for you and actually have them as valid geometric regions. Okay. So on top of those operations, we also added, some of the standard measures. As you can imagine, we added a function to compute the Euler characteristic as well as the genius. So in this case, you take, a cube, it's under it, and a torus. You can actually essentially compute the genus. We compute the genus automatically. In this case, we tell you it's 1. The genus of a torus is obviously 1. So those two objects are topologically equivalent, roughly speaking. So you can actually look at those pages. And what we did also, we extended, as you can imagine, Euler characteristic to work on meshes of any mesh, essentially, from dimension 0 to 3. So in short, this is kind of what we provided for Polyhedron. But also what we did, as I earlier said, we also added a little bit more constructor. One of the constructor we added, and which still in under construction, is uniform polyhedron. So there is a whole variety of uniform polyhedron, roughly speaking, 75 well-known uniform polyhedron. So what we try to do is to take those uniform polyhedron and introduce them to the system. It was an extensive work, especially that most of them are geometrically not well defined, because you have holes, voids, and lot of degeneracy, which are not per se cleanly defined for our geometric framework. But if you, for example, do an entity list, you'll get a bunch of polyhedron, and you can actually just use uniform polyhedron to return you those polyhedron. In this case, you have the cube, a regular dodecahedron and such. So we try to generate the actual right geometric object, without self-intersections, with planar faces and no degeneracy. So that's kind of one of our criteria for if a polyhedron or a closed geometric object to be a valid region. So uniform polyhedron have a collection of 75 of them, which are kind of clean and valid polyhedron. There will be a blog, soon, which kind of will describe that more in detail, as well as all the requirements in terms of defining a polyhedron, and we kind of tell you the whole story behind that. Okay, before we actually close, I will just show you one useful example. As earlier, I show how you can take an image, move to geometry, and from geometry use graph to actually solve an actual problem, the art gallery problem. So in this case, I will also show how you can use the new optimization framework, Convex optimization framework, to actually solve geometric problems. So in this case, how to find the analytic center of a convex polygon, which is essentially the point inside the polygon that maximizes the product of the distance between each side. So one first thing you want to do is, in this case, we generate a random convex polyhedra polygons. So I will just generate that one. So I will use linear optimization and actually use the property inequality constraint to actually get the set of inequality we describe my polygons. So here, this is kind of what the hyperplane representation or the H representation of your polygon. So you can represent the polygon as a intersection of hyperplane. So in this case, half line, right? Actually, in this case, lines, as you see here. So you have that nice representation. So you can use linear optimization to get that set of inequalities. And from that set of inequality, you can actually solve the optimization. You can rephrase the analytic center problem as an a conic optimization problem and actually solve it. And all this is possible with the new functionality we have in version 12 from Convex optimization. So that kind of show you how you can move also from geometry to another area to actually be able to solve geometric problems. Okay, well, there's a lot of functionality we added. I will suggest you to go to look at our guide page. This is a new guide page for polygons, where we give you all the representation of polygons, and the center point there is the canonical polygon, which converts it to that canonical representation, all the constructor, and the general class decomposition. I didn't talk here, where we have few function about to check if a polygon is convex or simple, and all the measure operation and Boolean operation we have actually working on the polygon. So that includes polygon with holes. Now you can imagine you have also the same for polyhedron, the canonical representation, the constructor and the operation, as well as the measure and other functionality. So you can look at our marketing page, sorry, our guide page, which have those structure and kind of give you a general idea of the set of functionality we have there for polyhedron and polygons. Okay, that's pretty much all for today. I will suggest you to actually join us every Tuesday and Thursday around the same time, 12 p.m. Central Time, for other twist talk about the new functionality in version 12. Thank you.